Hello, welcome to this video. Today we're going to do this problem, which was problem 6 on IMO of 1977. So it goes like this. We need to find all functions from f, that are from the natural numbers to the rational numbers, and satisfy f of n plus 1 is bigger than f of n for all natural numbers n. Okay, so I'm just going to jump straight into the solution. So what we're going to do is prove this thing. So we're going to show that for all natural numbers n and k, if n is bigger than or equal to k, that then follows that f of n is also bigger than or equal to k. So it's sort of monotonic, but like this side is not f of k but just k. So let's prove this. And I'm going to do it by induction on k. So for k is equal to 1, obviously f of n is bigger than or equal to 1 since f of n is a natural number. So this case is done. Now let's assume that it's true for k and look at the case for k plus 1. So suppose we have some n that is bigger than or equal than k plus 1. That means that n minus 1 is bigger than or equal to k. That means that f of n minus 1, by our induction hypothesis, is also bigger than or equal to k. But then again, something is bigger than or equal to k, then f of this is also bigger than or equal to k. So f of n minus 1 is bigger than or equal to k. But now, we know f of n minus 1 is smaller than f of n. We know this is true. So, we can say that f of n is bigger than k. But if f of n is bigger than k, that means f of n is bigger than or equal to k plus 1. Meaning that we proved this. But now from here we can get something very nice, which is f is strictly monotonic. So f of n plus 1 is bigger than f of n, which is bigger than or equal to f of n. And why is this inequality true? Well, f of n is obviously bigger than or equal to f of n, but now this is our n, and this is our k. So something's bigger than or equal than this k, then f of this is also bigger than or equal than this k. So f of n is bigger than or equal than f of n. And so we have f of n plus 1 bigger than f of n, so f is strictly monotonic. So the series, so you can think of it as a series goes like this. We have f of 1, which is smaller than f of 2, which is smaller than f of 3, which is smaller than f of 4, and so on. But now from this, if f is strictly monotonic, we can say something like this. If we know that for some m and k, if f of m is bigger than f of k, we know that tells us that m has to be bigger than k. Because if m were to be smaller than or equal to k, we would have, by f is being strictly monotonic, f of m would be smaller than or equal than f of k, which is a contradiction. By our assumption, f of m is bigger than f of k. So we know this is true, but now look at what we have here. F of something is bigger than f of something, meaning that this thing is bigger than this thing inside the f's. So we get that n plus 1 is bigger than f of n. But now, notice something. Here we used f of n is bigger than or equal to n to say that f of this is bigger than or equal than it. But this works in general for any natural number. since n is bigger than or equal to n, in this case, this n is sort of our k, we know f of n also has to be bigger than or equal to n. So f of n is smaller than n plus 1, but is bigger than or equal than n. And since f of n is a natural number, we know f of n has to equal n for all natural numbers n. And finally, that's it. And that's it. Since we finished the problem, we proved that the function f has to be the identity. And the identity function, so f of n is equal to n. And you can also easily check that here, n plus 1 is bigger than n, which is obviously true. So that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.